What about if we have resistors in parallel? In this case, notice that each of these resistors has the same potential difference across it. Their tops are connected, their bottoms are connected. The total current drawn from the battery will be the sum of the currents through each resistor. We could use Ohm's law to find that I equals V over R. So I1 is V over R1, I2 is V over R2, I3 is V over R3. The total current is the sum of these individual currents, or V over the equivalent resistance is V over R1 plus V over R2 plus V over R3. We divide by the common value of voltage to see that the equivalent resistance, 1 over the equivalent resistance, is the sum of the reciprocals of the resistors. This is what we got for capacitors in series. Here the equivalent resistance is smaller than the smallest individual resistance. Now, one thing you may have heard is electricity takes the path of least resistance, and that's wrong. Electricity takes all paths but an inverse proportion to their resistance. So yes, if you have a piece of plastic and a piece of copper connected between two different voltages, far more current is going to flow down the copper than the plastic, but there will be a tiny amount of current along any path. Now, we can do what we did with capacitors, where we look at a system of many resistors and see how could we identify the voltage across and current through each one. How could we replace this mess first with a single equivalent resistor? We're going to do the same thing that we did with capacitors. We're going to combine the individual pieces. The top two resistors are in series, so they just add, and we get 300 ohms. The next four are all in parallel, so we combine them with the reciprocal rule, 1 over 300 plus 1 over 400 plus 1 over 500 plus 1 over 600. And we get this number here. Is this the equivalent resistance? No. This is actually 1 over the equivalent resistance. That's why I left the units out, because if we kept the units in, we'd see we have inverse ohms here, and we'd know we're not done. When we take that final reciprocal, we get 105.3 ohms. So that's what these four are equivalent to. We can call the 700 ohm resistor RC if we want, but it's by itself right now. It doesn't much matter. The last two are in parallel, the 800 and 900. So we combine them and we get 423.5 for their equivalent. So now if we redrew it, we would have four resistors in series, RA plus RB plus RC plus RD. We add them up, we get 1528.8 ohms. So that one single resistor would look the same to the battery as this massive pile of resistors. The current through that battery, and therefore the current the current through that resistor, and therefore the current leaving the battery, would be 24 volts divided by that resistance, or 0.0157 amps. If that's the current leaving the battery, it all has to go through the 100 ohm resistor, the 200 ohm resistor, and we can find the voltage drop across those. The voltage drop across the first resistor would be I1 times R. 100 times this is 1.57 volts. Through the 200 ohm resistor, we get I2 is again 0.0157. We multiply that by 200 and we get 3.14 volts across it. When we get to the four resistors in parallel, that current's going to split up. We know that the current through our imaginary resistor that's equivalent to those four would still be this 0.0157. So the voltage across it would be 0.0157 times the equivalent resistance, which would give us 1.65 volts. If we now want to find that means the voltage is going to be the same across R3, 4, 5, and 6. So what's the current through each one? Well, V equals IR is the only thing we have to use. So the current through each one is the voltage across it divided by its resistance. And we see, not surprisingly, that the lowest resistance takes the most current, the highest resistance takes the least. If we add these four currents, you won't be surprised to learn that we get 0.0157 amps again. Just like if a river split into four branches and then came back together, we would expect it to still be carrying the same amount of water. The 700 ohm resistor has to carry the full battery current by itself, so V equals IR tells us 11 volts is dropped there. The imaginary RD is 0.0157 amps. So the voltage across it, we multiply by resistance of RD, we get 6.65 volts. So the voltage across both R8 and R9 is 6.65, meaning the current is split like this. A little bit more through the 800 than the 900 because they're very close to the same. If we add these up, we get the same total current. If we add up the voltage dropped across each of these resistors or resistor groups, we get 24 volts to within rounding error. Now, just as with capacitors, when these resistors are in parallel, we can't add the voltage across each one because that wouldn't make any sense. We just add the voltage that's across both of them. When we do this, this is the same if we go back to the height analogy, as saying if we have 4 separate 10-foot ladders scattered around a room going from the first floor to the second floor, that doesn't mean the first floor is 40 feet tall. They're all 10 feet tall. The first floor is 10 feet tall. We could now look for the power dissipated by each resistor with P equals IV, or P equals I squared R, or P equals V squared over R. However, if you use this last one, keep in mind that the full 24 volts is not the voltage for any of these resistors, and the full current of 0.0157 is not the current through those resistors that are in parallel. You only use the V or I that's appropriate to that particular resistor.